Good morning, students. This video is a little unique in that it's going out to both my earth science and environmental students. The environmental students, we have about 6 students left in the class since most of our seniors have left at this point. You guys were just wrapping up a unit on fossil fuels and energy resources. Our freshmen in the earth science classes, they've just wrapped up a unit on weather. With that in mind, I'd like to take the last week and a half to 2 weeks we have left, talk exclusively about something that naturally follows both of these classes, what you have been doing, and that's climate change. So we're going to talk a little bit about that today. And we're going to, this will be the first of 3 videos. You'll have notes to fill in for these videos. That set of notes will be your last assignment for the year. You also have a minor assignment that has some math attached to it that'll go out with this presentation. So let's get started. I don't want to waste any time. First thing, this thing is what my environmental students will recognize as a systems diagram, where it's actually representing climate change as an interaction between 4 separate systems: human activity, climate change itself, climate characteristics, and the threats to climate change. We'll come back to this diagram in the future videos. Right now, I'm just presenting it to you to see right early on. So there's 5 essential questions that we're going to answer over the next 3 videos. What is climate? How do we know climate change is happening? What's causing the climate to change? How will climate change affect our planet? And how can we mitigate the effects of climate change altogether, right? Now, as you know, climate change has become somewhat politicized in America. In fact, America is one of the only places where we have such a large proportion of people that don't believe in climate change. It's kind of, I wouldn't say exclusive to America, but certainly more prevalent here than most everywhere else. And for you earth science students, this kind of reminds us back to when we talked about flat earthism. We get this consistent scenario where the people who tend not to believe in climate change maybe aren't so educated in the facts, either because it wasn't presented to them when they were in high school, because this is kind of a phenomenon we've only really known a lot about in the last 20 or 30 years. So you have that. You also have, this is one of the situations where it's so politicized because even our political leaders often pass on misinformation. And we see it everywhere. We see people that certainly believe that it's a hoax or a fraud. We have politicians that parrot the same things. However, most, if not all, of our scientists are relatively in agreement that it's happening. And there are some disagreements as to why, but even the ones, for the most part, we have 97% of scientists saying that it's actually human caused. But if you see in that graph, most Americans maybe don't agree with that for a variety of reasons. So I want you to think about where you stand on this issue. It's kind of a somewhat humorous meme here, where you have someone contemplating, is climate change real? Is it real but just a natural process? Or is it something man-made, fossil fuel related that we're contributing to? And of course, at the bottom there, do we become fossil fuels in the future? And so I want you to really think about these 3 beliefs on the board that are kind of contradictory in some ways. And I want you to think, which of these claims do you personally mostly adhere to? If you're a freshman, you know in Freshman Connect, we're talking about confirmation bias, the tendency for people to ignore evidence that contradicts the beliefs they already have and only listen to the evidence that confirms the belief they have, right? So it's important for you to recognize what your beliefs are before you learn about something. In this case, which of these 3 claims do you most agree with, even if you're not sure why? The first says the global temperature has not been increasing during the last 200 years. That's one claim. The second claim is the global temperature is naturally changing and not primarily due to human activity. And the third claim is the global temperature is changing unnaturally fast, and it is primarily due to human activity. Well, we're going to focus primarily on that first claim today as we answer the first 2 of our 5 questions. So let's start with what is climate. Now, if you have your notes open, you'll want to follow along from this point forward, as this is number 1 on your notes, this question. So what is climate? What is the difference between weather and climate, first and foremost? And really the difference is a matter of time scale. when I ask this question to freshmen, I typically get the answer climate is an average. And maybe that's not the most detailed answers, but it's not incredibly wrong. Weather is a series of events that can change over time. You can have a hot day, you can have a cold day, you can have a rainy day, a dry day. Climate is the average over time, a long period of time. So you have two graphs here. One is the one on top shows weather as wiggles, and you see climate as the green line that averages those wiggles out. Below that, you have a seasonal variation because, of course, we know that weather changes with the seasons. Climate does not. Okay, so just because it's winter here and we have snow, and then it's summer and dry the next, for the next season, it doesn't necessarily mean that our climate has changed. It is not. It's something that you see year in and year out. So again, I have this question: can it rain in a desert? And the answer is yes, absolutely. The desert is the climate. It can still have rainy, wet weather. Um, Climate is the average. Okay, so you see that definition there. Climate's the average weather of a particular place in the world for long periods of times. Now, the thing is, climate is controlled primarily by temperature and precipitation, and in some ways, temperature, ultimately heat from the sun, controls it all. So the temperature and precipitation that an individual place has is primarily controlled by latitude, ultimately. You can see this image where it kind of represents the surface temperature of various parts of the world. And you see a trend where the equator certainly seems to be the hottest, the poles are much cooler. So you see this situation where latitude has a big influence on how hot it is on Earth's surface. Altitude is another one. Certainly, if you're high up, higher altitude, it's going to be much colder, and it could be drier, could be wetter, depending on the situation. The other big factor that controls temperature and precipitation of a climate is both the global winds, so air currents, and the global oceanic currents. So wind and water currents are both two big parts here. You see kind of a I don't know, some sort of shape here near the Arctic Circle, just southeast of Greenland. And you see that it's a little bit warmer in that part, kind of between Greenland and the UK and Scandinavia. Partly that's primarily it's oceanic currents that's responsible for that increased temperature as it moves up. And we'll talk. I guess we should have talked about oceanic currents already for both of these classes. Unfortunately, due to the COVID epidemic, that was something we're not able to cover this year and talk a little bit about that. The important thing to recognize is that even if the climate in a place is changing or on the Earth is changing, that doesn't mean it's changing the same everywhere. So here's an example of 2015 temperature minimums and maximums. And what you see is that even though it got much hotter than it's ever been before in some places of the Earth, most places of the Earth, there were places where it showed the coldest temperatures recorded. You see that just southeast of South America. You also see it just south of Greenland. So just because on average a place might be getting warmer, that doesn't mean it's getting warmer everywhere. That's an important part to know. Just like climate, we know climate is an average of weather. The same goes when we're talking about location here. So let's move on to the second question, which will be the last one we're covering in this video, but will be quite extensive. How do we actually know that climate change is happening? Again, the belief that we're addressing in this video is whether or not climate change is real, whether or not it's happening, and not some hoax generated by the media, right? So let's go back to this diagram. Recognize that this is showing temperatures only from 2015. So it's showing record warm and record cold areas. There's only a few spots, but you can see most of the Pacific Ocean there and the Gulf of Mexico is showing the record warmest temperatures ever during this year of 2015. And that's an interesting trend because if you look at this, the last 5 years we have also been the highest temperature 5 years ever recorded in all of human history. We have never seen 5 warmer years than the last 5 years. 2016 was the warmest year on record. This past year, 2019, was the second warmest. Before that, it's 2015, 2017, 2018. All of the last 5 years are in the top 5 warmest years ever. and that is pretty significant. So obviously, we can see that at least lately, there's certainly been a very noticeable trend, right? But it's not just lately. This graph shows if you go back from 2019 all the way back to 1880, you'll see that the most recent 2 decades every 2 decades has a different color, with the most recent being red, the oldest being blue. And when you put all of these seasonal trends on top of each other, you can see the x-axis shows months, where you see highs in June and July and lows in December. What you're seeing is a seasonal cycle where every single year we go from these dark blue older years to the much more recent red years, and we see them climbing and showing this nice rainbow pattern as a result. So in general, we should say, every decade at least since 1880 has been getting considerably warmer. Now, why is that? Why 1880? Well, the 1800s is when we first had the Industrial Revolution and when we first started burning coal. That is not a coincidence, as we'll see a little later. So the thing is, it's just, it's easy to say, okay, things are increasing in temperature if you're only looking at one data source. And again, those who claim that this is a hoax ignore the fact that everywhere around the world, various different countries, various different scientific agencies are all measuring the same trend. So what you see here is an animation of various different organizations all measuring the same trends. Again, 1880 is about the time we also invented the thermometer. And so what we see is that these temperature records we have for the last 150 years or so are very accurate, because they've been recorded independently by people all over the world, with various biases, of course, and various other allegiances, but they still are all recording the same thing. And that should say a lot. So um, let's look at that record. Here are the recorded temperatures, recorded directly with thermometers since the mid 1800s. And we see this one has four data sets that we're largely in agreement globally what the average temperature has been. And you can also see this baseline here where it says 0 is set at pre-industrial levels, or right around that time, what the temperature had already been for thousands of years on average. Obviously, we see an increase here. This graph is sometimes called the hockey stick graph because it shows the sharp increase, but it's not nearly as, I should say, dramatic as some of the other graphs that we might look at here. And that's actually kind of important, right? We have, you know, it's important for us to be able to look at a graph like this and say some important things about it. The problem is people use graphs, they portray them and deliberately, I should say, maybe false ways, or maybe they focus on certain things to make the graph say what they want, right? So, for example, if I zoomed in on some part of this graph and I just looked at that trend, you might say, oh, there is no increase in temperature. Actually, in some ways, it seems like temperature is going down, right? If I just looked at that one moment in time, right? So it's important for us to be able to expand outward, right? So if we're saying global warming is happening, certainly in this graph, it seems indisputable. It's important for us to be able to zoom out even further to make sure that this trend compares to the years before. The problem is we didn't have thermometers before 1880 or so. So how can we tell if this trend we're seeing is something unique to what we're experiencing right now? And there is a way to do that, which we're going to talk about right now. How can we measure the temperature of the Earth before thermometers were invented? So I want you to think about how we measure things in the past, in the present, and the future, because there are ways to at least predict or approximate variables, even if we can't directly measure those variables themselves. So direct measurement is something we do for the present. If I'm taking a measurement of something, it's something that's occurring right now. The past, we use something called proxy indicators, and we predict the future, at least the future of future trends of certain variables using scientific models. So again, a direct measurement is using a device to directly record a variable in the present. This could be using a stopwatch to record running speeds. We have seismograph listed here and some other weather instruments in the far right. Direct measurements obviously are the most accurate. because you can directly measure something as it's happening. However, the accuracy depends on those devices working properly. If they're not calibrated, they might give you false results. Otherwise, extremely accurate way of measuring things. So our use of a thermometer to measure temperature in the last 150 years, we'd say that's incredibly accurate because it used a device at that time. Now, how about the past? If we're going to measure the variable as it occurred in the past, we have to use something called an indicator, an index, or proxy indicator. We've seen this before in this class, whether we called it this or not. A proxy indicator is a measurement of related variables to estimate the value of a different variable from the past. So if I can't directly measure the temperature from a long time ago, what I want to do instead is find something that changed with temperature that existed a long time ago, and then look at those changes, right? So tree rings are a great example. As a young kid, most of us are taught that tree rings show how old the tree is. You just count the number of tree rings, you know how old the tree is. That's an approximate estimate. It's a proxy indicator. You can't actually measure how old a tree is directly unless you were born before there and you were taking measurements until it died, right? No, instead use a proxy indicator to tell how old a tree is. The thing is, tree rings can actually tell us a lot about climate specifically because the width of the tree ring tells you whether or not conditions are favorable for that tree, if there was enough water, nutrients, if it was too hot or cold. So you see that example here. This is a tree from Virginia, and it shows periods of drought and famine, and also periods where the tree did very well based on the size of those tree rings. That's an example of proxy indicator. We've looked at rock layers as a proxy indicator of Earth's age before. When we looked at in earth science, at least, and environmental science, you probably remember this from Canan's class. We can look at a fossil, and we may not be able to have the equipment to directly measure how old it is with like carbon dating, but instead, what we can do is we can look at the positions of the rocks, determine what order they formed in, and try to use that information to get an approximate date from when that fossil was deposited. So that would not be another example of a proxy indicator. Now, there are several proxy indicators we use to estimate the past climate. So again, before 150 years ago, when we invented the thermometer. So boreholes, one thing that we know is that the temperature under Earth's surface is very slow to diffuse. And so if you drill a hole deep into Earth's crust, the temperature of Earth's surface is in some ways preserved in the rock temperatures drilled below. So if you drill down at Earth's surface, you can get a rough estimate, at least, of the temperatures that used to be at Earth's surface. The problem with this is that Earth's like lithosphere, Earth's crust, the temperatures might change wildly in the atmosphere year to year in a way that doesn't affect the temperatures in Earth's surface. So that's one way that might complicate the data. And if you just relied on borehole data alone, you're probably not going to get a very accurate estimate. You really can only use these for the last 500 years or so because of the way that the Earth's crust retains heat. As mentioned, we can use dendrochronology, tree rings, to try to give an estimate anywhere from hundreds to 1,000 years old. Some trees are very old. Coral rings, and in some ways, other fossil organisms work the same way. You can use a measure of growth to determine how warm or cold it was at any given time. Again, if you're only relying on tree rings and you're not matching it up with anything else, your estimate's probably not going to be very accurate. Ice cores are one of the primary ways we do it right now, and I'll talk about that a little more detail in a minute. That's useful almost up to 1 million years, so you can get quite a bit of information from ice cores as far as what the temperature used to look like. Marine sediments, also useful up to 200 million years, which is quite a bit. Marine sediments kind of have an end. You'd think that they'd be around forever and that we could just test them, but because Earth's crust primarily is going to be subducting at these convergent oceanic plate boundaries, we know that we kind of have a time limit when we can test sediments. The way we test sediments is very similar to ice cores, so I'll wait a moment before explaining. Finally, fossil plants and algae. As long as plants and algae have been around, There have been ways that they give us clues to Earth temperature, from the amount of pollen released in ancient history to a number of algae. There's all kinds of ways that we can use fossil plants and algae to give us some estimates, and they are one of the oldest estimates we can actually get. So let's go back to talk about marine cores, or ice cores and marine sediments. Here's an ice core. In our next video, I'll talk a lot more about this process of obtaining ice cores. It is fairly intriguing, but let me explain some of the theory behind it right now. How do we get temperature data from ice or water? The thing to keep in mind is not all water is created equal. And when I say that, what I'm talking about are isotopes. So water contains hydrogen and oxygen atoms. You see a diagram to the right, an oxygen atom, two hydrogens. That oxygen has 8 protons, 8 electrons, 8 neutrons. However, what if you get an isotope of oxygen in your water molecule? And that does happen. Now remember, an isotope is a form of an element that has a different number of neutrons. So you see that there's such thing as a heavy water molecule, represented as water molecule B here, that where the oxygen actually has 10 neutrons instead of 8. So oxygen 16, and again the number stands for the mass here between our neutrons and our electrons. You see that oxygen 18 here, we have a collection. I'm sorry, I said electrons and neutrons. It's protons and neutrons. Oxygen 16 is the normal form of water that we see on the planet. Oxygen 18 in the water molecule is the less common form of oxygen that we see on the planet, but it still gets turned into water. So think about that. We have 2 different water molecules. One's way more common than the other. Which one do you think is going to be more likely to evaporate? Which one do you think is going to be more likely to condense as precipitation? Because it makes a difference. It turns out that the heavier water is more likely to condense into a liquid and fall as rain, which is why we find heavy water in warmer, rainier climates, or at least we find more of it. It's really only a 5% difference or so between our polar and tropical climates as far as this relationship. But it is a very striking relationship. You can see on that graph, there's quite a clear correlation between temperature and the proportion of this heavy water isotope. So that relationship, we can get a mathematical formula describing this curve here. We can use that mathematical relationship to project what the temperature used to look like. So this is how we use this as a proxy. And again, here's an illustration that shows how we have water that's going to evaporate. The heavier isotope tends to precipitate more as warm air rises and moves towards the poles. By the time some of that air, that moist air gets to the poles, I shouldn't say a lot, but a significant amount of the heavy isotope water is already condensed and formed as precipitation. So there's less that gets to the poles where we take these ice cores. So it's important for you to recognize how we do this. It's with isotopes. And again, marine sediments are the same way. You can compare isotopes that are typically found in warmer areas compared to cooler areas to get some sort of relationship with temperature. So the thing about proxies is, one, you need to be able to take lots and lots and lots and lots of data for it to be accurate, right? If you're just looking at one tree ring, for example, that doesn't tell you much. If you look at 100 tree rings or 1,000 tree rings, that's going to give you a lot more information, right? The other thing is using more than one proxy method, and you take an average of that, is going to improve your accuracy. So relying on, even if it's 100 tree rings you looked at, that's still not a great prediction you're going to make about the past temperature range. You need to look at all of the different predictions made, come to a happy medium, an average, and see how that stacks up. And that's what we've done. On this graph, you can see each color represents a different proxy method. So one might be tree rings, one would be ice cores, one would be marine sediments. And you can see that even though some of these are more extreme than others, so example, that light blue line, it has the same peaks and valleys as the other lines. They're just more extreme up and down. Even though you see that, you still see that there are similarities, but where they go up, where they come down, and that the most likely estimate is somewhere averaging all of these lines together, right? That's how we use and we come to our proxy, um, or how we use proxy indicators to come to our approximate estimate of what the temperature used to look like. And by taking the average, we can get pretty close to what it used to look like. And the same goes for if we're using models to look forward in time. Now, the thing to keep in mind, so here's another example of that hockey stick graph, right? It's straight most of the ways, and then it curves up violently as we get to the industrial age, and that black line represents actually measured temperatures. Um, One thing to keep in mind is, again, the farther we zoom in or out, the more we're saying about our actual trends over time. So this is the last 2,000 years. Is that a good estimate? Should we continue backing out? We have proxy data for, we know for, in some cases, hundreds of millions of years. What happens if we go even further and look at the temperatures? So here are two graphs. The one on top represents 800,000 years ago. So the thing to keep in mind here, guys, that last graph we were just looking at here, right? This is 2,000 years, basically a sliver at the end of this one, right? And so some of you looking at this might say, wow, I mean, it looks like temperature has kind of changed relatively regularly every 100, 150,000 years or so. And that is definitely true. Our temperature goes through these cycles over time, which we'll talk about in the next video very often. In fact, right now, we're certainly right at the edge of what should be a temperature maximum. Although we're kind of at the point where temperature should start to fall down again relatively soon. And when I say relatively soon, I mean in the next couple thousand years or so. Um, However, that being said, remember that last graph is just a sliver of this. So really, what we're seeing in that graph doesn't really confirm that what we're seeing is natural. In fact, it's quite the opposite for reasons I'll explain in a minute. This whole graph at the top fits into this point at the bottom. So you can see where that kind of matches up, and you can see it used to be a lot warmer, and then it overall started cooling down, even though it got more variable in climate over time. So climate variability is certainly something that we've seen on our planet, although typically that variability, again, is something that you see in cycles of 100,000 years, right? So with that in mind, I want to point out that even though that last sliver was meant to represent, the last 2,000 years or so, right now, we're at 2020. The 2050 mark is represented by this dot here, and what the predicted 2,100 mark will look like is way up there, way, way higher than anything we've seen in the last million years, way higher than we've seen in the last 5 million years. Right now, we're at temperatures that we have not seen on a global average for the last 150,000 years, back when hippos used to be in England. Obviously, that doesn't happen now, but we are ramping up fast. So even though we have these global cycles, the rate at which we're going up right now has not been seen before. Certainly, we have no data of it ever being seen before. So let's think about those projections in the future. How do we come up with those? We do that with a scientific model, which is just a mathematical or graphical representation of some system that we can use to make predictions about how things might change or about the future itself, right? So a model can just be a diagram. Again, there's a systems model on the right-hand side there. It can be a graph as well. Here are some old models. Some of these are from like the 60s and 80s. Some are more recent here that you can see projected here. The actual temperature is represented in red. So see if you can see any models here that are relatively accurate. Right away, the ones that stand out are those in green, our IPCC, which is our climate change panel. It's an international panel on climate change that looks to see how things might progress. And that line they've kept straight as an average. And you can see that despite the ups and downs in our global climate, they've relatively maintained that global average that you see again represented in green. Now, a lot of these other projections are not so great. So Kellogg, for example, thought we'd be increasing much faster. All the ones in blue, you see people that thought that we were going to time out, that our Earth was going to bounce back and start cooling itself off. And there's a lot of reasons that's not going to happen, which we'll talk about a little bit tomorrow when we get into the mechanics of this. So how do we determine which models are better than others? Well, again, just like with proxies, more data will improve the accuracy of your model. And typically, when it comes to models, that means more time. Every year, models get better. Certainly is true of our climate models. Some of those really weird ones were from a long time ago. The most accurate ones are the most recent. The other thing, again, just like proxies, using more than one method to model it and then finding the average is going to improve your accuracy. So on this diagram in the light blue is a sample of several different models, the range, maximum and minimums, and those ranges have been averaged to get some sort of mean prediction from several different models. And so you see that here. And so that mean and the black line actually follows our red line pretty closely, give or take, some spikes up and down along the trend. So let's recap as we close things up here. Okay. One, scientists use a combination of direct measurements, proxy indicators, and models to measure and predict changes in climate. Two, direct measurements are indisputable, at least if you can assume that their machines were working correctly. Climate is rising. We know this. We've been measuring this the last 150 years. There's no controversy whatsoever that it's going up. Now, if we expand that out to the last 2,000 years, we're still going up. If we expand that to the last couple million years, it's maybe thrown more in question, which is why we have to rely on some other data, which we'll talk about now. Proxy measurements, which we use for those past measurements, indicate that the climate is hotter than it's been since 150,000 years ago. And again, our climate change understanding and the data we use to come to that understanding gets better every year, right? So as far as our three claims here, global temperature has not been increasing during the last 200 years. Consider that myth busted. There is absolutely no data that could possibly support this. Certainly, there could be false data supporting it. But we've become very much in agreement on this. The temperature has been rising very consistently. We don't know to what extent it's going to rise in the future. Again, we have to rely on models for that. And there's still a question as to who's to blame. And that's what those next two beliefs are concerning, which we're going to cover in the next two videos. We talk about the mechanics, climate change, how it works, and also what to do about it. This will be it for me. Thank you for tuning in. Please make sure you fill out your notes and go ahead and finish that assignment for today, and then we'll be done. Thank you.